Electricity has been moving in the world since clouds first formed on Earth. Lightning is a form of electricity. It's electrons moving from one cloud to another, or jumping from a cloud to the ground. As a species, we watched this, we observed it, and then we learned how to harness it through circuits. Understanding electricity and circuits, which are such a big part of our lives, starts by understanding something very small, the atom. Everything in the universe is made of atoms. Every star, every tree, every animal, the human body is made of atoms. Air and water are too. Atoms are the building blocks of the universe. Atoms are also so small that millions of them would fit on the head of a pin. Atoms are made up of even smaller particles. The center of an atom is called the nucleus. It's made of particles called protons and neutrons. The protons and neutrons are very small, but electrons are much, much smaller. Electrons move around the nucleus at a great distance from the nucleus. If the nucleus were the size of a tennis ball, the atom would be the size of the Empire State Building. Atoms are mostly empty space. Electrons are found in the invisible clouds on energy levels. They're held in these levels by an electrical force. The protons and electrons of an atom are attracted to each other. They both carry an electrical charge. Protons have a positive charge, and electrons have a negative charge. The strength of the positive charge of the protons is equal to the negative charge of the electron. Opposite charges attract, holding the atom together. Electrons require energy to be able to escape their attraction to the nucleus. Electrons closer to the nucleus require more energy to be removed from the atom than those further away from the nucleus. If these outer electrons get just a little extra energy, they can escape to other atoms. When the movement of electrons is in mostly one direction through an object, the movement is called electricity. Conductors and insulators pass along these electrons differently. Conductors are the types of materials that have electrons held loosely in their outer energy levels. Because they're held loosely, they can be pushed along easily. That means electrons flow very easily, passing along that negative charge. These are materials like metals, silver, copper, and electrolytes such as salts. On the opposite end is insulators. Insulators hold on to their electrons very tightly in those inner energy levels. That means they're very hard to push along. It takes a lot of energy, so electrons do not flow very easily. This prevents electrons from flowing. We see this a lot in plastic, rubber, air, and glass. This is why a lot of electrical equipment is either insulated or coated with rubber or plastic. When electrons are allowed to flow through these conductive wires, this LED lights up, transforming from chemical energy in the battery to electrical energy to radiant light energy. If you try to close the circuit with some tap water, the LED barely lights up. This is because water on its own is not a strong conductor. Electrons flow, but not as freely as when salt is added to the water. The electrolytes released in the salt water prove to be a better conductor than the water alone. We can apply this observation to make our own conductive Play-Doh using some common household items. All you need is some flour, lime or lemon juice, vegetable oil, food coloring, salt, and some tools to mix them up. I'm going to roll this dough into a basic circuit. Electricity travels in closed loops called circuits. It must have a complete path before the electrons can move. If a circuit is open, the electrons cannot flow. Electricity makes our lives easier, but it can seem like a mysterious force. Measuring electricity can be confusing because we can't always see it. We're familiar with terms such as watt, volt, and amp, but we often don't have a clear understanding of these terms. We buy 60-watt light bulbs, a tool that needs 120 volts, and vacuum cleaners that use 8.8 amps, and we don't ever stop to think about what these units mean. Our first measurement is called voltage. The pressure that pushes electrons in a circuit is called voltage. Voltage is a measurement of the pressure applied to electrons to make them move. It's a measure of the strength of the current in a circuit, and it's measured in volts. This tool is called a multimeter. It's able to measure the voltage of our circuit. As the two leads get closer and closer together, the voltage drops. Measuring the voltage directly from the two ends of my battery helps to explain why this is called a 9-volt battery. It has an electrical potential difference of 9 volts. Voltage is the force that pushes the electrical charge through the circuit. This force works like the pressure in a hose. If you increase the water pressure, you increase the force pushing the water through the hose. Increasing the voltage creates a greater force because you're creating a greater difference in potential charge that pushes along those electrons. The potential difference between these 2 points changes because of resistance. Resistance is a property that slows the flow of electrons, or the current. Resistance acts like friction, slowing down the electrons. Resistance is measured in units called ohms. There are devices called resistors with set resistances that can be placed in circuits to reduce or control the current flow. Every load in a circuit has resistance. This includes lights, motors, etc. Think of the circuit as a highway. The cars act like the electrons passing their charge through the circuit. Traffic acts like the resistance in that circuit. A toll booth or a car accident can increase traffic and slow down the flow of cars. Similarly, all electrical loads have resistance and slow the current or flow of electrons. The resistance in the Play-Doh slows down the electrons. Cutting the Play-Doh stops the electrons. Bridging that gap with an LED shows us the electric current. The LED only works when aimed in one direction, so the current must be flowing in one direction. The electric current is the flow of electrons. It can be compared to the flow of water in a river. A water current is how much water passes you in a given time, whereas an electrical current is measured in amperes or amps. 1 ampere is 6.25 times 10 to the 18 electrons per second passing through a circuit. Voltage, resistance, and current can be visualized by watching Winnie the Pooh. Pooh Bear trying to move through the hole is like the current flowing through a circuit. Rabbit applies a force to help Pooh move through the circuit like voltage. Unfortunately, the tight hole acts like resistance, slowing Winnie the Pooh down as he tries to become unstuck. We can explore the relationship between voltage, current, and resistance through Ohm's law. V is our voltage, measured in volts, the electromotive force, or the potential difference between 2 points on that circuit, is equal to I times R. I is our current, measured in amperes or amps. This is the flow of electrons. Times our resistance, measured in ohms, or the omega symbol. This reduces the flow of electrons. At individual points within a circuit and the circuit as a whole, you can examine and calculate using this relationship, Ohm's law. This is an example of a basic circuit. If you're able to open and close the circuit, you've made a switch. When I close this gap with another LED, I've created a new kind of circuit, a series circuit. Series circuits are named because each load is placed in a row. The electrons have to flow through one single path, through all loads. The resistance of each load adds up as they cause the voltage to drop more and more each time. Because of this single path, the current flows at the same rate throughout. If you add more loads, notice that the brightness of the LEDs drops. The current acts like a highway. If you add more tollways, the traffic slows down. Removing any of these LEDs stops the flow of electrons, and the whole circuit dies. A series circuit is like building a tollway on a single-lane highway. All cars have to travel through all of the toll booths in a row, slowing the cars down. The cars have no optional path, just like the electrons have no optional paths. This creates one steady current, with different voltage drops across each resistor. If we wanted to explain the series circuit mathematically, we could say that the total resistance in the circuit is equal to the sum of all the resistance in the circuit, since each electron has to travel through every single resistor. The total current is equal to the current at any given point. It's the same flow of electrons throughout the whole circuit. There are no other paths. And then the voltage of the power supply is the addition or the sum of the voltage drop across every single resistance. Every resistor or every bulb, every motor is going to cause a voltage drop as the electrons pass through. We can apply Ohm's law in our series circuit tendencies with this schematic diagram. Here I have a battery and 3 resistors. So I'm going to find the total resistance to begin with. Total resistance equals the sum of all resistors. So 6 plus 4 plus 14 gives me a total resistance of 24 ohms across that battery. I can now find the total current. Whenever I see 2 out of the 3 variables in my Ohm's law equation, I can always find the third. Substitute in what you know. It's a little one-step equation. Divide by 24, and the current is 0.5 amps. At this point, I can double check. Can I apply any of my tendencies? I've found the total resistance by adding all the resistors. Well, I know the total current is equal to the current at every other point throughout. And I know the total voltage will be the sum of all the voltage drops. So I can apply right now the total current at each point. Then I see now I have R and I at each point. I can apply Ohm's law again. I'm going to substitute in what I know, solve for what I don't, and keep repeating it until every V, I, and R is solved in the circuit. I can even double check my work. 7 plus 3 plus 2 equals 12 volts. Electrons travel through a path of least resistance. So if I add a line of Play-Doh here, the electrons will go through it instead of the LED. If I add an LED to this new Play-Doh, I've created a parallel circuit. Parallel circuits are named as such since electrons follow multiple or parallel paths, not just one. Since electrons can travel through multiple paths, the voltage is always the same or constant across each load. As I add resistance to the circuit, the LEDs do not drop because the resistance is inverse. Because of this, the current is different along each rung of the parallel circuit, which looks like a ladder. If I remove LEDs, the electrons just simply take another path. So you can remove an LED from a parallel circuit without the other bulbs turning off. A parallel circuit acts like a multi-lane toll booth. The cars now have optional paths, so they travel through each booth at different speeds. Optional paths for electrons create differing currents. Even though the cars travel at different speeds through the booth, they're all pushed along by the same amount of cars behind them on the road. As the electrons flow at different currents, they still have that same voltage pushing them along through each of the paths. To help apply Ohm's law, we can explain these tendencies mathematically. Because of that inverse relationship with resistance, the inverse resistance of the total circuit is equal to the inverse resistance of all other resistors in that circuit. The current is the sum. Because we have multiple currents, you have to add them up to get the total current. It's not the same throughout. And then the total voltage is the same at every single point. This is why parallel circuits allow bulbs or loads to continue to work even if another resistor or bulb was removed. We can apply Ohm's law and the tendencies to this parallel circuit. I see 3 resistors in a row. They kind of look like a ladder. That's parallel. I'm going to take those resistances and add their inverses, or 1 over. Now that gives me the inverse of my total resistance. So it's not 0.5, but 1 over 0.5 gives me 2 ohms. Whenever I see 2 out of my 3 variables in Ohm's law, I can always solve for the third. I know voltage, I know resistance, so I can calculate the current. Substitute in what you know, solve for what you don't. Now at this point, I need to try to apply my tendencies. We already found resistance using our inverse button on our calculator. The total current is the sum, so those other 3 resistors all have to have currents that add up to 6. And then I know that the voltage at the power supply for the whole circuit is equal to the voltage drop at
each of those resistances. So that means that 12 volts, 12 volts, and 12 volts at each point, because we have that equal force, that equal push of electrons through each one. Now we can apply Ohm's law. If I have two variables, I can solve for the third. Substitute in, solve for what you don't know. Substitute in, solve for what you don't know. And yet again, substitute and solve. You can even double check your work. 1 plus 3 plus 2 is 6 amps. I expected a total current of 6 amps.